Okay, everybody, welcome to Physics Day. We're starting Newtonian mechanics, which is putting to use all these kinematics equations that we have been studying for the last couple months. So, the first thing we want to talk about is Isaac Newton. Do you guys know about Isaac Newton?
He was a great man.
Yeah, he was a great man. He was smart, not just smart in physics, but he was also street smart. So in his time, was the time of the bubonic plague. You heard of that?
Yeah, that's a
Yeah, so he was smart enough to get out of town. So he went to a farm house away from the population, and he sat around for many years waiting for the plague to be done. And that's where he wrote his book, The Principles of Nature. And he has three laws. The first law, anyone know what Newton's first law is? Yeah, I call it the Energizer Bunny couch potato law. The books say an object that is in motion or tends to stay in motion, and an object that is in rest tends to stay at rest unless acted upon by an outside net force. The kind of simple way to say it, I would say, is an object tends to maintain its state of motion. And that kind of wraps it up. So if it's at rest, it's going to stay at rest. That's what I call couch potato, right? Because you don't get off the couch unless your parents act upon that. Get you off your couch, off the couch. And then the Energizer Bunny just keeps going and going and going, right? So that's Newton's first law. So in other words, if I'm here on the Earth, and I'm on the top of a mountain, and I have a big cannon, and I shoot a ball, well, let's make the cannon that way. I shoot a ball through the cannon. Newton's law says that this goes in a straight line forever, never, 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 past the moon, past everything. Unless acted upon by a net force, right? So what is the net force that acts upon this?
Gravity.
Gravity. In what direction is gravity? Towards the center mass of the big mass, in this case. Very good. Exactly right. So it's in this direction. So that will affect the y velocity, and it'll change the y velocity, and we'll get this parabolic shape. If we didn't have gravity, then it would just keep going forever and ever and ever, at whatever speed it's at. But since we have, if we go by a moon out here, is that going to affect that? If it happened to go by the moon, what would happen? It would go like that, right? And it would get forced towards the center of the moon. Question. So this first law is also called the law of inertia. Inertia, okay? And inertia then is this tendency for an object to maintain its state of motion. So the question is, how do you know the difference between objects? Because I got a car moving down the road, right? And that car is cruising along at, 30 meters per second. 30 meters per second, that's pretty fast, right? That has a tendency to maintain its state of motion, right? And then I got a little tiny bug, and it's moving that way, and that has a tendency to maintain its state of motion too. So the question is, how do you distinguish between these two? Because you know there's a difference, right?
Yeah, one's very reference.
Okay, reference frame, one's bigger than another, and the last comment. So, mass is the measure of inertia. Okay, so mass is the measure of inertia. Okay? And when we do things in mass for physics, we use kilograms as our base unit. You know, grams is a base unit as far as SI, but kilograms is what we use because we're massing things like cars and planets. And so kilograms is what we use for all of our formulas. Which makes sense, right? If I have more mass, I'm going to have more tendency to maintain my state of motion, right? It would be a little bit harder to push me around than it would be to push, Martine around, right? Question. Okay. So, Newton's second law. Anyone know about Newton's second law? Okay. Let me ask you this. Do you guys remember the definition of acceleration?
Yeah,
The change in velocity per time, right? Okay, so I got a question about acceleration. What causes an acceleration? You know that? Okay, so if you want to accelerate something, you go up and you push it, right?
Yeah.
Okay, so another word for a push then would be a force. Okay, a force is defined as a push or pull. Okay, so how does acceleration relate to force?
It's
Directly proportional. Okay? Which means that as force goes up, my acceleration goes up, right? Okay. How does acceleration relate to mass? So if you try to, force me versus forcing a tiny bug, which one's going to accelerate with the same force? More. The bug, right? So how does mass and acceleration, how are they related if the force is constant? Indirectly, right? Well, it's actually inversely is the word that we want to use. Inversely proportional to mass. So if you were going to put these two things into a formula, or these three things into a formula, you would say acceleration is equal to, and what would you do on top? Force, right? And what would be on bottom? Mass. And so, if your denominator gets bigger, this side's going to get smaller. And that makes sense, right? According to what we did. So this actually is what we call Newton's second law. And it's the acceleration is directly proportional to the force applied to an object and inversely proportional to the mass of the object. Now, when Newton first explained this, he explained this as a change in momentum. So he said force was equal to a change in momentum. And momentum is a mass velocity. So here's a side note. Newton said that force is equal to a change in momentum per time. And momentum is mass times velocity. And so think about it, if a baseball gets thrown at you at 10 meters per second versus 20 meters per second, which one's going to need a bigger force? The 20 meters per second, right? As long as you have that time in there, and we'll talk about that more when we get to momentum, but this was his first description of force, this change in momentum per time. If you just do some substitutions, you get this force equals mass times acceleration. And better yet, the summation of forces equals mass times acceleration. Okay? And we'll talk about this math here in a little bit. I want to define the forces for you first. So we're going to talk about the math with this here in a little bit, but first I want to define the forces. So in the forces we have contact forces, which Sheldon mentioned that we never really do touch anything, which is right because the force of electricity is so strong that we can't get through that to actually touch anything. That's true, but we do call it contact if it feels like we're touching something. So you push on something's electrons and those electrons push back on your electrons and you feel that. That's a contact force. And then there's field forces. So I'm going to, for contact, I better put touch in parentheses just to make sure you understand. It's the feeling of touching. The field force, though, would be where there's no contact. For example, you guys said magnetism is a field force. So you can see magnets move without them touching something. Or you can see something metal move under the influence of a magnetic field. What else do we have? Gravity is a big one here. Gravity. Okay. And another one that you probably aren't aware of, light is not a force. No, light is packets of energy. Another one that you're probably not aware of right away, but you probably, if you have wool socks in the winter in North Dakota, you walk around on the carpet and then you go up to your sister and touch them in the arm, right? And what do you get? A transfer of electrons. So the force of electricity is a field force too. Okay. So those are 3 field forces that you need to know. Okay, so how do we use Newton's second law mathematically? So, do you guys know what summation means? Summation means adding. Do you agree? So, summation of forces equals force 1 plus force 2 plus force 3 and so on. Does that, or what is force? Do you guys know? Does it have direction or not? Force has a direction, so force is a vector. Okay? And keep in mind, we determine the direction of vectors through the signs. And in any problem, you can only have positive and negative, which is, any individual math problem, we can only have positive and negative. Otherwise, we can't do the math with our conventional math. So, let's look at it. Here are a couple examples. If I have a force of 10 newtons, and I have a mass of 2 kilograms, okay, and I'm on a smooth surface, which means you neglect friction. The question is, what's your acceleration? Well, it's the summation of forces. Is there anything other than 10? Well, there's always the force of gravity, but it's completely perpendicular to this force. Do you agree? So they are independent of each other. X and Y are independent. So I know that this thing isn't going to be accelerating down here. How come? What's canceling out that force of gravity or stopping it from falling? Well, the table, right? Otherwise, the thing would be accelerated if there was a net force. So we don't have to worry about that yet. So we're talking about the summation of forces in the x direction. So it'd be 10 divided by 2. My acceleration would be 5 meters per second squared in this direction. Does that make sense? Okay, well, let's look at one that's just a little bit different. Okay, so let's have that same 2 kilogram box. And we'll say that we have 10 newtons of force here. But this time we'll say that there is friction. Okay, so the thing with friction is, little definition, friction only and always opposes motion or potential motion. So that's the definition. You have to memorize that. You have to know that. Friction only and always opposes motion or potential motion. Okay, so in this case, the potential motion here is to the right. Do you agree? So if I have friction, it's going to have to be in that direction. Unless this thing is already moving, then that could be a different story. But we'll just say that the v sub naught here is 0. Okay, so let's say that I have a friction of 8 newtons. Keeping in mind there's another force on this. What force is always on everything? Gravity. So we have the force of gravity, which is 20. So we have to have the force of the table in the opposite direction, which is 20. Otherwise, the thing would be going up or down. Okay? So, in this case, then acceleration would be the summation of forces divided by the mass. In this case, it would be 2 newtons to the right. Do you agree? Because the summation of forces is force 1 plus force 2. Force 1 is a positive. I usually put to the right positive, or at least whatever the main force is. You know, I would never say friction is in the negative force, or is in the positive direction. So, plus this friction, which is in the negative direction, equals 2 newtons in the positive direction. Does that make sense? So it's a summation, but once you start putting the directions in there, then you can subtract the numbers. Okay, so the question was, how did you know the force of gravity was 20 newtons? Well, I'll tell you, weight is a force, and weight is the measure of the pull of gravity on a massive object. Yeah, weight is the measure of the pull of gravity on a massive object. So you guys might be wondering what the force of gravity equation is. The force of gravity here is the gravitational constant, which is big G. And this is a universal constant. So when they looked at all the things in the movements that they could measure in the universe, they came up with this fixed number that put the right kind of twist on the numbers so they would all match. So this is a gravitational constant, and this is the relationship between the masses. So m1 times m2 times that universal gravitational constant divided by the square of the distance between the center of the two masses. So this is the force of gravity, big G, m1, m2 over r squared. So if this is the force of gravity, and Newton said that a force causes a mass to accelerate, do you agree? Now this whole mass 1, mass 2 thing matters. Because if we solve for acceleration here, okay, so let's say we were going to solve for acceleration, we're going to cancel this mass out. And this mass would be like the small mass. So I'm canceling out the small mass over here, and I'm left with, what would this mass be? That'd be the mass of the Earth. Well, because I'm solving for acceleration here. So I started out with mass times acceleration, because force equals mass times acceleration, Newton's second law. This is the definition of the force of gravity. So when I solve for acceleration, I would get this. Big G, m of the planet, over the radius squared. And this radius is from, you know, if the planet is completely regular in its density, it would be from the center of the planet to the center of the mass of a person. So this here would be the definition of the acceleration of you and I if we fell at a distance away from the center of our mass. So let me ask you this. if this is the surface of the Earth, how far up does our space shuttles and things orbit? Like maybe that far? So where are we at? In the mountains and stuff. Well, maybe like that high? Or I can't even get that close with my little smartboard. We're basically right here on the surface. Do you agree? So if you think of this curvature of the blue ball that we're living on, where is the center of that going to be? It's going to be quite a ways down. Do you agree? So this radius here doesn't change, really, for you and I. And the changes that happen are very, very, very small. So if you put these numbers together, what do you think you come up with? Like, yeah, 9.81 meters per second squared, right? So that's where our little g comes from, is 9.81 meters per second squared. That's what we've been using in our kinematics equations. Well, we've been using 10. Okay, but that's where little g comes from. And so, since we never really change our radius, then we can say that little g is our acceleration. And we can say that the force that causes our mass to accelerate is little g, or it is a multiple of our mass of little g. And that is called weight. Okay? So if I have a 2 kilogram object, the weight of that object is 20 newtons. And I'm using 10 for little g. Okay, so that's our weights. So why do you think we don't use the SI way of weighing people in America? Well, because no one wants to be like, 800 newtons. How much do you weigh? 800? I mean, we just don't do that in America, right? But they do that in other parts of the world. This is the standard definition for weight. Okay, so those are some good questions. Just to kind of extend our forces. So we talked about contact force, and now I want to tell you like some labels for some other forces. So we talked about weight, force of gravity. Here's another one called tension. Okay. So we talked about weight, we talked about friction. Those are two forces. Now tension is another force we're going to use a lot, and that would be the force through a rod or rope. The force through a rod or rope. Okay, so that'd be like if you're pulling on two sides. So if I have a rope here and I'm pulling this way, and I have another rope here, another person pulling this way, that force that's transferred through this rope or rod is called tension. Okay, so you need to know the tension force. Another one that you're going to need to know would be another force that you're going to need to know is called the normal. Okay, and that's an old construction term. And the first definition of the normal is that it's perpendicular to the surface. That's where this construction term, that's why we called it normal. So if we have a box sitting on a surface, we know there's a force of gravity, right? And the reason why it's not falling through the surface is because of this normal force. So in this case, the force normal, so there's two definitions to normal. The first is it's perpendicular to the surface. So you can see this is at a right angle to the surface. And the second is it's the force that the surface applies to the object so that the object does not fall through that surface. which is pretty easy to determine on something like this. It's just going to be equal to the weight. But what if I have a ramp? Right here, I have the force of gravity, right? But that's not the normal force because, well, first of all, it's not perpendicular to the surface. But remember, if we split this up the way that we learned how to split up our vectors, we could split this into a right triangle this way. This here would be the force down the ramp. So it's not a real force, but it's the part of gravity that is forcing this box to move down the ramp. And this would be the part of gravity that's forcing it into the surface. So your force of normal then would be equal to in magnitude of this, okay, but opposite of it because the surface has to push on the box so that it doesn't fall through the surface. Okay, and then as far as friction, we have two different types of friction. If the box is static, we call this the force of static friction. So this friction would be keeping that in place. So static means there's no movement. If the box, though, has enough force down the ramp, so let's say that that's the force down the ramp, this is the friction, then that thing's going to be moving down the ramp. Do you agree? Because the force down is bigger. So this would be force kinetic, or friction, kinetic friction. So they're both friction. One is when the thing's moving, one is when it's not moving. Okay. Okay, so hopefully this helps you with some definitions and some guidelines to do some introduction math with Newton's second law.